Shearing metal from a solid block requires an immense application of kinetic energy. At the point of contact, the machine must generate enough mechanical stress to force the material past its yield point. This resistance is defined as the cutting force. It is the primary variable that determines tool life, final surface integrity, and the total energy consumption of the machining process. This force is dynamic, shifting in response to the interaction between the machine's spindle, the tool's edge, and the specific crystalline structure of the workpiece. Transitioning from standard aluminum to high-strength aerospace superalloys introduces severe unpredictability. These difficult-to-machine materials require massive increases in force that can quickly exceed the mechanical limits of the tool. Managing these forces is a prerequisite for predictable tool life and dimensional accuracy. Without precise modeling, the energy required to shear advanced materials rapidly accelerates tool wear and can lead to immediate mechanical failure. Systematically controlling these forces requires a first principles model to map and predict the physics of the cut. This model organizes machining into three controllable domains. First, kinematic parameters define material removal volume and traverse rate. Second, tool geometry dictates how edge angles penetrate the material microscopically. Third, the tribological environment alters friction and heat generation using cooling and lubrication. Process optimization depends on isolating these three variables and balancing them to minimize resistance. We begin with the foundational kinematics of material removal. Within this domain, depth of cut is the most significant factor because it directly scales the cross-sectional area of the material being sheared. Here, a tool removes a metal layer. Depth of cut defines its thickness. The relationship is linear. Increasing removed volume places a proportional load on the tool. Akgun's 2022 research found this depth accounts for 81% of total cutting force variance. While depth is mathematically predictable, the effects of cutting speed are nonlinear, deeply complex, and strictly governed by thermal physics at the contact point. This graph represents Mohad Noor's 2021 study on Hastelloy X. As cutting speed increases, force drops initially. High-speed friction generates intense heat, triggering thermal softening that reduces yield strength. However, at extreme speeds, mechanical forces rise again, creating a high-force zone. Eidin's 2023 findings suggest an optimal sweet spot exists just below the tool's nose radius to minimize the total power required for the cut. While depth dictates the raw volume of the cut, speed acts as a thermodynamic trigger. Engineers must find the exact velocity where thermal softening maximizes efficiency without exceeding tool thermal limits. We now move to the microscopic level to examine the second pillar, tool geometry. The physical shape of the tool edge is under constant pressure. As the edge blunts, the physics of the engagement changes. Peng Li and Cheng's 2022 research analyzed how this increase in the edge radius, or the roundness of the tip, affects force distribution. Comparing a sharp versus a rounded edge, the rounded tip increases feed force, the backward resistance, much faster than downward tangential force. This geometry drives high stress concentrations deep into the material, ruining surface integrity and introducing internal defects. One geometric solution involves the inclination angle, as detailed by Popak and Anisimov. Here is a tool with zero inclination, meeting the material at a vertical 90-degree angle. By tilting the edge, kinetic energy is redirected. This mechanical change reduces overall tangential force and can double the machine's productivity. However, tool wear continuously degrades these precise angles during the machining cycle. To counter this, Kara's 2024 work highlights cryogenic treatments. Cooling tools to ultra-low temperatures hardens the carbide, maintaining these sharp geometries for much longer periods. Geometric tuning directs the kinetic energy of the cut. By optimizing angles, engineers protect the workpiece by redirecting mechanical loads away from the finished surface. The final pillar of the model is the tribological environment, cooling and lubrication. Fluid serves as a mechanical friction modifier rather than a simple thermal heat sink. It acts directly on the interface between the tool and the workpiece to reduce the energy required to complete the shear. Comparing dry machining against minimum quantity lubrication. MQL uses a precision spray, injecting minute droplets directly into the shear zone's point of contact to alter the friction coefficient. Reducing this friction mechanically lowers the force required to cut. Oslu's 2025 research found that using MQL with aluminum oxide-coated tools creates an optimal low-friction barrier when cutting titanium alloys. However, lubrication follows a curve of diminishing returns, as shown in Konya and Kovacs's study on flood cooling. This graph tracks oil concentration in the coolant against cutting force. Force reaches its absolute minimum at 12% concentration, maximizing shear efficiency. Beyond 12%, excess fluid gets trapped between the tool and part, inducing hydrodynamic vibrations that destabilize the cut. Environmental controls are precision instruments. Insufficient lubrication destroys the tool edge, while excess fluid destabilizes the physics of the cut. Advanced machining is a constant negotiation between material removal rates and the physical limits of the tool. These three pillars are deeply interconnected. Changing one variable without recalibrating the others will lead to unpredictable forces and process failure. This integrated model maps all variables simultaneously. Every slider must be calibrated to the workpiece. Optimization requires aligning the depth of cut, thermal softening speed, edge geometry, and exact lubrication. When balanced, the process achieves minimal energy consumption and maximum tool protection. Trial and error manual adjustments are insufficient for modern aerospace-grade materials. The future of precision manufacturing relies on using these first principles physics to engineer a mathematically optimized cut.